All right, so we're still in chapter, oops. Oh man, it's gonna be one of those. Chapter 7, section 4. So we got a couple more examples to wrap up this section. So remember, this section was on partial fraction decomposition. So we'll be facing integrals that are one big ugly fraction, a rational function of some kind. And our goal is to try and separate this into the addition or subtraction of smaller, simpler fractions such that each one of those is easy to integrate or relatively easy to integrate. Because as it stands right now, this thing is a nightmare, right? So nothing good can happen here. Okay, so luckily the denominator has already been presented in a factored form. That in itself is sometimes a lot of work. So we were spared that part of it, but it's still going to be a lot of work to figure out how to break this up, how to break this whole thing up. Okay, so first we have to think about the setup for this thing. So the pattern, I'm going to go off to the side here and try and figure that out. So we have, actually I'll put it right in here. So ignoring the integral for a second, I'm just trying to work out this fraction. I have 1 minus x plus 2x squared minus x to the third power all over x squared plus 1 to the third power. Okay, so as per the patterns for partial fraction decompositions, this guy is linear, this guy is quadratic, right? So the linear ones are going to command their own fraction with one constant up in the numerator. It's called a constant a. Okay. And then the ones that are quadratic, like this one, are going to command their own. Oops. Oh, that's a squared, not a cube. That makes it even uglier. Okay.
Professor, are you recording?
Yes.
I don't think you're recording, right? Okay.
I hope so. Come on. Should be yes. Stop recording. Yeah, should be recording. Thanks for checking. That's always a nightmare. Spend a bunch of time and never record it. Okay, so as per the pattern, this is linear. This is this term x by itself is linear. So it demands its own fraction with a constant up in the numerator. And now this guy's quadratic, and there's no way to further factor that without going into imaginaries, right? So this guy is going to demand its own fraction as well. And we have x squared plus 1. And up in the numerator, we will have a linear pattern plus c. Right? So when the denominator is linear, then the numerator is going to be some constant. When the denominator is a quadratic, then the numerator is going to be linear. Okay? And now we have to take care of the fact that it's squared. It's duplicated. Okay? So because it's duplicated, we have to kind of run up to it. We have to build up to that power. So this one is to the power of 1. The power of 1. So we have to have another one that's x squared plus 1 squared. And then it will also have its own linear equation up here. Maybe C, D, and say E. Good. Now it doesn't have a 3 there, but just to make sure that it's super clear what this pattern is, let's pretend for a moment that this is a cubed. If the original question had a cube there, we would need a power of 1, a power of 2, and then we'd keep going and also have a power of 3. Like that. And then this guy would have its own linear equation. G. Like that. So pretty ugly. Luckily, we don't have to go to the cubes because this one stops at a square. Good? Good. If instead, just to really hammer this home here, if this had been x to the power of 5, x plus 1, like that, then, and something up here, doesn't matter what's up there, then we'd have to have 1 for x, and then we'd have to have another one for squared, and then we'd have another one for x to the third power, and then we'd have to have another one for x to the fourth power, and then we'd have another one for x to the fifth power. Pretty ugly. And then we'd have 1 for x plus 1, and luckily that one only has a power of 1. Unless we also throw in a 2 in there, just to make it extra fun, and then this one would be x plus 1 squared. Good. Luckily, these are all linear, linear, linear. So in this case, these would all be A, B, C, D, E. The patterns are good. So, all right, well, good enough. And this guy is also a squared. Squared. Okay, so pattern isn't nearly as bad as it could be, though it's still not that great either. Okay, so here's our setup. I'm just going to copy it down. Copy it down one more time. X plus 2x squared minus x cubed all over x times, x squared plus 1 squared equals, and then capital A over x, and leave some space there. Actually, that's fine. Bx plus c all over x squared plus 1 plus dx, my b and my d. dx plus e all over x squared plus 1 squared. Okay, so I'm going to multiply both sides of the equal sign by the denominator, x times x squared plus 1 squared, and then on this side multiply everything by x times x squared plus 1 squared. Then when I distribute, multiply there, multiply by there, multiply by there. On the left-hand side, everything cancels, giving me just the 1 minus x plus 2x squared minus x cubed equals 2. Now when I distribute, then this x cancels with that x, giving me capital A, x squared plus 1 squared, plus, and then I get a bx plus d times, and then when I distribute, I have an x, and then only one copy of the x squared plus 1 survives, right, since one of them will cancel with this, since it's squared, plus dx plus e times, and then both the powers of x squared plus 1 cancel with that one, so it's just an x that survives. Good. Okay, so we end up with 1 minus x plus 2x squared minus x cubed equals 2. So got to FOIL everything here. This is going to end up being x to the power of 4 plus 2x squared plus 1. And then this is bx plus d times x cubed plus x. We're going to have to FOIL that next. And then we end up with a dx squared plus ex.
Professor, that d next to b should be a c, I think.
Oh, man. Oh, thank you. Yes, that's good catch. This should be a C. That should be a C. A C. Good. Thank you. Anything else? Okay. All right, so then we distribute this guy, and we'll end up with ax to the fourth plus 2ax squared plus a plus, and then when I FOIL this guy, let's put it in green, get this times that times this times that. So we'll get b x to the fourth power plus a bx squared plus a cx cubed plus cx, and then these guys, plus dx squared plus ex. Cool. Okay, so now the next clue to this, the next key to this, is to regroup them by powers of x. So I have all the terms that have powers of x to the power of 4. This is that one and that one. I'm going to group those up together, put them right next to each other. Then all the things that have cubes. Okay, so there's only one. That's good. That'll make things easy. Then all the things that have squares. So this one has a square, this one has a square, this one has a square. And then all the things that have powers of 1. This guy and this guy have x to the power of 1. And then there's the last survivor. The only thing that constant that doesn't have a variable at all is this guy. Good. Okay, so let's just regroup them over here. Looking at the powers of x, I'll end up with b plus a. Oh, a plus b. A plus b times x to the power of 4. And that takes care of this guy and that guy. Then there's only one term that has an x cubed. So plus c x to the power of 3. Took care of that guy. And then all the squares, there's 3 of them. There's going to be plus 2a plus b plus d x squared. So 2ax squared, the bx squared, and the dx squared. Done. And then there's only 2 terms that have powers of x to the power of 1. We have c plus e times x. That takes care of this guy and that guy. And then we got the lone survivor of plus a at the end. Good. That takes care of all of them. Okay, so that we have to counterbalance with the left-hand side. And just to make them match, I'm just going to start moving them around a little bit. So I'm just going to put them in descending order. So I have minus x cubed, and then plus 2x squared, and then minus x plus 1. Just switch them around in descending powers. And also I see that I have an x to the power of 4. So I'm just going to introduce that in there. I'm just going to toss it in there, and I'm allowed to do that as long as I also multiply it by 0. 0x to the power of 4, right? You can always toss in an extra term as long as you're multiplying it by a constant of 0. Minus x to the third power plus 2x to the second power minus x plus 1. Good. Okay, so now the real genius part here is when we marry these. In order for the balance, this equal sign, to remain true, it must be true that the left-hand side equals the right-hand side. So if we look at the constant in front of the x squared, x to the fourth power, it must equal the constant in front of the x to the fourth power. So from there, I can conclude that the a plus b must be equal to 0. Just up there. So from there I can conclude that a plus b must be equal to 0. Good. The constant in front of the x cubed part is this c, and well, there it is right there, c. So from there I can conclude that c must be negative 1. That's going to make that easy. Okay. And then next, the constants in front of the x squared are right here. So from there, I must be able to conclude that 2a plus b plus d equals to positive 2. Next, the constant in front of the x must be that guy. So I can conclude that c plus e equals negative 1. And finally, we ran out of colors. I don't know. How about light blue? Finally, it must be true that this guy, the constant, must be equal to that guy. Capital A must be equal to positive 1. Any questions about any of that? Okay, so luckily this system seems pretty easy to solve. I mean, first of all, we already have one of them. Yeah, question? Ooh, sorry, I couldn't make that out. Try one more time. Yeah, Zoom is failing us. Do you want to try typing it in? Yeah. Okay. So remember, all of this is being recorded and posted online. So if you miss something, you can always get it from there once it goes up. Was that all you needed for me to scroll up, or was there a... All right, so this system is actually pretty good, pretty easy to solve, since the value of A is right there, is a 1. The value of C is just negative 1. And now we can easily find a few of the other ones. Since we know the value of A, we can easily come over here, grab this guy, and say, well, A plus B is 0, but the A was a positive 1, plus B is 0, so B must be equal to negative 1, so that's already 3 down. Okay, then from there we can grab this guy, and we know the value of C, so C plus E is negative 1, but we do know that C itself is negative 1, plus E equals negative 1, so therefore E must be equal to 0. We have another one. And now the only one that's missing is D. So from here, let's grab this guy and get through all the traffic and write it down over here. A to A plus B plus D must be 2. And we know that the A was equal to positive 1, 2 times 1, plus the B was negative 1, plus D must be 2. So this will be 2 minus 1 is positive 1. 1 plus D equals 2. Therefore, D must be equal to positive 1. Good. So 1, negative 1, negative 1, 1. Okay, so coming up to here, now we know that this is a positive 1. This guy was a negative 1. This guy was a negative 1. This guy is a positive 1. And the E was a 0. Good. So now that I have all those constants, then I can rewrite the original statement. You know what? Let's put it up here. So now all of this work lets me know that, in fact, 1 minus x plus 2x squared minus x cubed all over x times x squared plus 1 cubed can actually be rewritten as 1 over x plus negative x minus 1 all over x squared plus 1, and then plus And we have x squared plus 1 squared and just x up there. Make sure that I got the right constants down here. It was 1, -1, -1, 1, and e. Yep. Okay, so just gotta make sure that I substituted it the right way. So we figured out a way to separate this really ugly fraction into 3 smaller, less scary fractions. Good. Okay, so now I'm actually ready to integrate this problem. So now I'm ready to go. And so now that was all scratch work. Now I'm ready to do my actual integral. We have the integral of 1 minus x plus 2x squared minus x cubed all over x squared plus 1 cubed dx. Thanks to all my side work, I know that that's the same thing as figuring out the integral of 1 over x minus, I'm just going to factor out a little minus from there, minus, and then x plus 1 all over x squared plus 1, plus, and then we have x over x squared plus 1 squared. Good. Okay, and so this whole thing, dx. I'm going to separate this into 2 separate fractions as well. This whole denominator under the x, this whole denominator under the 1. So I'm going to rewrite this way. This is going to be equal to the integral of 1 over x dx. That's easy to figure out. Then minus the integral of x over x squared plus 1 dx. That's going to be easy to figure out. Minus the integral of 1 over x squared plus 1 dx. That's a standard integral. So that should be easy to get as well. And minus the integral of x over x squared plus 1 squared dx. And that should be an easy u substitution. So is this one. So let's let u equal to x squared plus 1. Then du dx is equal to 2x. So that means that du equals to 2x dx. Good. So I'm missing a 2. I'm going to pop it in here. Put in a 2 right there. And then balance it out with a 1/2. And that way I have my du. And I'm going to do the same thing over here. In fact, I have the same substitution going on here. Right? We have x squared plus 1. And so I'm going to put in a 2 there. And then also balance it out with a 1/2 there. Now this one I'm not going to do a u substitution on it. It's just one of our standard, I don't want people to get confused. So this is this for this guy, and then technically for this guy I'm going to do the same thing. I'm going to let, just to make sure no one gets it confused, I'm going to do a w substitution over here. X squared plus 1 dw dx equals to 2x, therefore dw equals to 2x dx. So I'm going to substitute this one with using the w variable. This one I'm going to leave alone because this is one of our standard integrals, right? This is just tangent inverse. So there's no work that needs to be done for that one. So this is going to be the integral of 1 over x dx minus 1/2 the integral of 1 over u du minus the integral of 1 over x squared plus 1 dx minus 1/2 the integral of 1 over w squared dw. Okay. All right, so then this one is just going to be ln of x minus 1/2 ln of u minus tangent inverse of x minus 1/2, and now this is negative 1 over w to the power of 1. Good? Questions, questions, questions? Remember, guess and check it if you get confused. Another way to think of 1 over w squared, come on, squared, is to think of it as w to the negative 2 power, right? So what function out there will give me a derivative equal to w to the negative 2? Well, that would be w to the negative 1. When we take the derivative of this, we bring down the exponent, we get a negative 1 times, and then w to the negative 1 minus 1. Good. So derivative with respect to w of w to the negative 1 is equal to this. And that gives me that almost, except there's that extra little minus 1 there. Right? So that's why we introduced this extra minus 1. Good, 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 good. Okay, so now we got to rewrite everything back in terms of x. Ln of absolute value of x minus 1/2 ln of absolute value of x squared plus 1 minus tangent inverse of x plus 1/2, and that's 1 over w, which was x squared plus 1. Good, good, good. I don't really see too many ways to simplify this, so I think that would be it. So don't forget to put plus a constant, and that would be our answer. Any questions or comments from anyone? Anybody see any obvious problems anywhere? Let's see if it matches with whatever the author did. All right, this is what the author did. Okay, so you take that guy, you take that guy, you break it up, zeros, ones. Okay, that looks familiar to what we did, similar. And we ended up with that. Yep, okay, so we ended up with the same thing when we broke it up, so that's good. And then that author, okay, also separated this and got that. Yep, that tangent inverse x, 1 over, yep, okay, so I just put a plus k there. Looks good, so we agree. Any questions, questions, questions? Is that a question trying to happen there? No, 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 no. Okay, last question or last example in this section is this one. So some rational functions can be changed into rational functions by, some non-rational functions can be changed into rational functions by means of appropriate substitutions. So in particular, when an integrand contains an expression of the form the nth root of g of x, then the substitution of u equals to the nth root of g of x may be effective. Other instances appear in the exercises. Okay, so as per their hint here, if we wanted to integrate this guy, Well, their hint is that maybe we should do a substitution that where we let u equal to this numerator and see if we can figure out a way to integrate that. So based on their hint, I'm going to say let's let u equal to the square root of x plus 4. Okay. What I want to do is square both sides. Right? I'm already thinking of some, it's not going to be a straightforward substitution because if I take the derivative of this as it stands, I'm going to end up with another radical, which is not in my integral here, so I won't be able to do a direct substitution, right? So, so if we square both sides, we end up with u squared equals to x plus 4. Okay. Then we can use implicit differentiation to figure out what this is. So let's take the derivative with respect to x d dx on this side. Come on. And then the derivative with respect to x on this side. So this will be 2u times du dx. Right, if you remember this is implicit differentiation because this is asking us to take the derivative of this function with respect to x, but this is not an x, it's a u, right? So we got to assume that it is a function of x. So we kind of apply our chain rule. Take the derivative of the outside function times the derivative of the u function with respect to x. Good. Okay, so now here, well, this is just going to be 1. That makes that easy. So we end up with 2u du equals to dx. So that gives us that. And then we have that. And then from here, we can get a value for x. U squared equals to x plus 4. So u squared minus 4 equals to x. Okay, so we have everything we need piece by piece. I figured out that the x is right here. I figured out, well, this was the original u right there. This u is that thing. And then finally, we figured out that the dx is this thing. Right? So when you do a substitution, you got to do piece by piece, make sure everything can be replaced, substituted, not just the main part of it. And now we're ready to do a nice substitution. So we have the integral of the square root of x plus 4 over x dx. And that's going to be equal to the integral of, and then we have our u divided by x, which is u squared minus 4, times the dx, which is equal to 2u du. Good. So let's pull out that 2 out here. No need to have that. And then we end up with the u squared. Integral of u squared over u squared minus 4. Okay, du. All right. Well, they're the same power. So my first thought, first thoughts are, let's see if u substitution works. Well, a substitution, so let's in this case say a w substitution. But the derivative will involve powers of 1, u to the power of 1, and then I would end up with 2 of them. Right? So is it clear to see if this had been a 1 there, things would be a lot easier. I would let my substitution be the denominator. Its derivative would be right there, so we'd be in business. But unfortunately, there's a 2 there, right? Because there's a u there and a u there. So another common instinct for people is to do this, and this is just bad math. They do that, they separate it this way, and then they try and do this, I don't know, this way, and I don't know what they do. They somehow magically a plus appears there. I don't know. So definitely not the right way to go, right? So don't do that. So, well, we are in partial fraction decomposition land, so maybe that has something to do with it, right? let's use the properties of partial fraction decomposition to figure out what this is. And my first thought is that the degree of the numerator is equal to the degree of the denominator. That means I can simplify it a little bit by dividing it. So I'm going to do u squared, and I'm missing the other power, so I'm going to toss in the plus 0u, power of 2, power of 1, minus 4, and that's trying to go into u squared. How many times does this go into that? Okay, so it can go in there once, one time. This times this gives you u squared plus 0u minus 4. No, I'm writing in blue. Right? And then remember, I'd like to distribute a negative 1 and add down. Negative 1, add down, and these are all plus 0. Plus 0u, plus 0. Good. So distributing a negative 1, that's just going to give me 0, 0. That whole thing is just 0. Distributing a negative 1 gives me a plus 4. Yeah, I don't know why it's red. Plus 4. Good. Okay, so that means that I can take this guy and say that it's equal to 2 integral of 1 plus 4 over u squared minus 4 du. Any questions about that? The ugly integral. Okay, well, this part's obviously easy to figure out. This part here, let's use partial fraction decomposition to figure out what this is. We can separate it out a little bit more. So I'm going to go off to the side here and work with this fraction. So I have 4 over u squared minus 4. Well, that is going to be equal to 4 over x, oops, not x, used to my x's, u plus 2, u minus 2, u plus 2, u minus 2. Okay, so based on our work with partial fraction decomposition, we know that this should be a case where one fraction has a u plus 2, and another fraction has a u minus 2, and then there's these two constants we have to figure out. There's a constant there and a constant there. Okay. Multiplying both sides by the denominator, u plus 2, u minus 2, cancel out with all that and just give me a 4 that survives, equals, and then on the other side I got to multiply everything by the same thing, u plus 2, u minus 2. So I end up with capital A times u minus 2 plus capital B times u plus 2. We're almost there. A equals to A times U minus twice A plus BU plus twice B. Good. So combining them in powers of U, we end up with B plus A. I don't know why it stuck it that way. I read it this way. U. And then the other constant, which is just going to be plus 2b minus 2a. Okay. All right, so from here we can conclude that these two must add up to 0. b plus a must be 0, since there is no powers of u over there. And we must conclude that the 2b minus 2a, that part must be a 4. Okay. Okay, so if we factor out a 2 and divide, we must conclude that b minus a must be equal to 2. Good. And then if we use this guy, we get that b must be equal to minus a. And then plug it into there, we get that b must be equal to minus a equals to 2. So minus 2a equals to positive 2. Therefore, a must be equal to negative 1. And if a is equal to negative 1, then back from up here, we get that b must be equal to negative 1 times negative 1. Right, since the a itself is a negative 1, and there was already a minus 1 out in front, so b equals to positive 1. Whole lot of work just to get a negative 1 and a positive 1. And all of that comes back to this guy to get a negative 1 and a positive 1. Good. You know, it's easy to get lost with all these, especially with these very limited screen things. Okay, so going back to the original, not the original, but back to this stage, I'm going to rewrite this as 2 times giant bracket. Okay, so then we have the first integral. That's easy. It's the integral of 1 times d, just du, right, plus, and then it's going to be, now I left the 4 there. I could have also, the other thing I could have done is I could have factored out that 4 and left the 1 there and figured it out, but I left the 4 there. So that's that whole thing. So the second integral is going to be the integral of negative 1 over u plus 2 and plus the integral of 1 over u minus 2 du du. Good. So this is going to be equal to 2 giant bracket, this is just going to be u, plus this is going to be minus, let's get rid of this thing. There's a minus there, so I'm saying minus ln of u plus 2 plus ln of u minus 2. Come on. Absolute value. Good. Now if we just switch these around, we end up with 2 bracket u, and then we get plus ln absolute value of u minus 2 minus ln of u plus 2. Now technically I shouldn't wait till the end. I should stick the plus c here so don't forget it, but technically it should be there at this point. So let's keep it here, plus c. And then I'm going to bring these two things together. Remember our properties for log functions. If they have the same log and we're subtracting, then we can rewrite it using division in the algorithm. So this would be 2u plus 2 ln of u minus 2 all over u plus 2 plus some constant. Now I'm going to put a little c sub 1 there because this 2, if I distribute it, distribute, it's really going to end up being 2 times this guy, right? So 2 times c, I'm going to call that c sub 1. It doesn't really matter. It's just some constant number out there. Good? Almost there, except that the original question was not written in u. The original question was about x, so we still have to come back over here and think about what x is. So u is equal to the square root of x plus 4, right, from here. Square root of x plus 4. So this is going to be equal to, well, let's rewrite our original integral now that we have all this space here. So now, and this thing is big. Integral of x plus 4 over x dx is going to be equal to this thing, 2 times, and now the u was square root of x plus 4 plus 2 ln of absolute value of square root of x plus 4 minus 2 all over square root of x plus 4 plus 2 and some constant at the end. Good. Questions, 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 questions? Let's see what the author did. Hopefully we match up. So the substitution that was suggested, tried that, good, solved it, got that, same thing, got that, same thing, got that, the same thing. We can evaluate it either by factoring it or using partial fractions, or by using formula 6. Okay, good. All right, so in yesterday's video, as we were solving one of these problems, we ran into a little formula for it, so then it becomes a useful formula we can apply whenever we see something that fits this form. And so we get this, and yeah, I think it's the same. Any questions? Okay, so that's the end of my PowerPoint for it, and there was a suggestion to do number 21, so let's try doing that one. Now, how can we get to it? 21. 21. Here it is, number 21. The integral of 1 over t squared minus 1 squared dt. So let me copy that down. This is here, what's that? Okay, this is chapter 7, section number 4, and this is going to be number 21. Number 21. And we have the integral of 1 over t squared minus 1 squared dt. Okay. So, t squared minus 1, that's something that can be squared, right? And first of all, is it okay if I just exchange this variable? I hate working with t's. My t's to me end up looking like plus signs, and particularly with this technology, everything looks extra messy. It like hiccups on me all of a sudden, and it creates these little blur things. And it's kind of hard to work with things. I can't even do straight lines sometimes. So how about if I change it over to, how about w? W is good. W squared minus 1 squared dw, right? It's just a dummy variable, right? Could be a t, could be an x, could be a y, doesn't matter, right? It's the concept we're trying to express. The letter we use is just a tool to express the idea. Good. Okay, so I like w better. All right, now working with w squared minus 1, that's something that can be factored. W squared minus 1 is a difference of squares, right? This is the same thing as w squared minus 1 squared. right? And we know from our work with factoring polynomials that whenever we see something of the form a plus b times a minus b, these are two conjugates. When we FOIL them all out, what happens? We get an a squared minus an ab plus an ab minus a b squared. The middle terms cancel, and we end up with a squared minus b squared, a difference of squares. So now if you want to go backwards and you notice, hey, look, I have a case where it's something squared minus something squared, we know what factors like that. That's how we can very easily and quickly conclude that this factors this way. Okay, so this guy factors, and it's getting squared. So I'm going to say that that is the same thing as w plus 1 squared, w minus 1 squared, all over 1 dw. Come on, computer. There, dw. Good. Okay, so now we want to try and figure out a way to rewrite this big, ugly fraction as the summation or subtraction of simpler, easier fractions, hopefully, that's the hope, such that we can figure out how to integrate it, right? Because as it stands, it looks pretty ugly, and I can't really think of a good solution. It would be way easier, right, of course, if there was a t here. If there was a t there, then I would let this be my u. Its derivative would involve something with a t, and then we'd be able to substitute it, right? But hopefully it's clear to everyone that because there is no variable t there, then it makes it harder. Good, good, good. Okay, so let's do a little bit of work with this guy. How do we figure out how to break this up? So that is going to be the fun part. Okay, so following the rules, luckily these are linear equations. So we have w plus 1 squared and w minus 1 squared, all of that over 1. So we know that w plus 1 merits its own fraction, plus, and then a w plus 1 squared would also merit its own fraction. This is linear, so it has a constant in the numerator. This is linear, so it has a constant in the numerator. Plus, and then pretty much the same thing over here. W minus 1 has a d, plus a w minus 1 squared has an e. Good. If this had been a cubed, then we'd have to go one more, right? So when we have a repeated factor, then we have to assign a different fraction to each one of those factors, starting with a power of 1, then a 2, then a 3, dot, 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 all the way up until you get to that power. Good. So I hope that pattern is good. So now to simplify this, I'm going to multiply both sides of the equal sign by this term, right? Multiply this side by w plus 1 squared, w minus 1 squared. So everything cancels here, leaving me just a nice, happy little 1 here. Seems like this is going to be an easy question, but then you peek on over to the other side and you go, no, this is not going to be an easy one. W plus 1 squared, and then w minus 1 squared, and then again we distribute, and we distribute, and we distribute, and we distribute. So for the first fraction, it'll be this fraction times both of those. So one of those powers will reduce. So for the first one, we end up with a capital A times w plus 1 to the power of 1 times w minus 1 squared, plus then we end up with b times w minus 1 squared, since now both of these terms cancel, plus, and then we end up with the d times w minus 1 times w plus 1 squared, plus capital E, and then w plus 1 squared. Good. Any questions, any questions, any questions? Okay, so we can see this is about to get really fun since we have to do a whole lot of foiling here. So I'm just going to take it one step at a time and leave that guy alone and foil this. So this guy right here, I'm going to foil as w squared minus 2w plus 1. Good. plus b times, and then this guy should be easy, w squared minus 2w plus 1 plus d times w minus 1, and then again I gotta FOIL this guy, FOIL that guy as w squared plus 2w plus 1, and then plus e times w squared plus 2w plus 1. Good. Wow, this is getting really ugly. If I keep going, we'll get to this thing where we got to keep foiling and then regroup them in powers of w and all that. But this might be a really great time to try the other way to solve these once you get to this stage. So let's poke around at that one for a second, because I think that method should lead to good things. So let's try that. Okay, so this is going to lead to the right answer if you keep going, but this is getting ugly. Keep going, but ugly. Okay, so let's try that other method, right? I'm always game to try a new method or a different method if it's going to work out well. So the other idea is to substitute values of w that are convenient, things that are going to cancel a bunch of terms out and make life a little easier, and either help us get to the values of a, b, well, how did I skip c? Oh, doesn't really matter. A, b, d, e. Good. Okay, so let's put that over here. I have 1 is equal to capital A, and then w plus 1 times w minus 1 squared, and then plus b, plus b, and then w minus 1 squared, and then plus d, w minus 1, and then w plus 1 squared, w plus 1 squared, man, it's ugly, plus e, and w plus 1 squared. Good. Okay, so what I want to do is maybe choose a positive 1 for w. Let w equal to positive 1. Right? So if this is an equality, so whatever happens, we get a new equation when w equals to 1. So when w equals to 1, lots of good stuff happens. This is going to turn to 0, this is going to turn to 0, this is going to turn to 0. Everything zeroes out. The only thing that survives is this term. Good. So I'll end up with 1 equals to a, and then this will be 2, and then this will be 0 squared, plus b times 0 squared, plus d times 0 times 2 squared, plus e times 2 squared. Okay? So lots of stuff goes to 0. That's a 0, that's a 0, that's a 0, and so we end up with 1 equals to e times 4. So we get 1/4 equals e. Good. Questions? Okay, let's try something else. How about -1? We'll let w equal -1. Let's see what else happens. We'll let happen? We end up with 1 equals to a times 0 times -2 squared plus b times -2 squared plus d times -2 times 0 squared plus e times 0 squared. So this whole term goes to 0. This whole term goes to 0. Come on. This whole term goes to 0. Come on. 0. And then we end up with 1 equals to 4b, or 1/4 b. Halfway there. But now, what do we do? What else would be a good substitution? Well, we've tried 1, we tried -1. A good one to try is 0. If we try letting this be equal to 0, things simplify easily. So let's try letting it equal to 0. Squeeze it down here. Let w equal to 0. So I'll end up with 1 equals to 1 minus 1 squared. 1 equals to a times 0 plus 1. 0 plus 1 is going to be 1, and then 0 minus 1 is going to be -1. So it's going to be 1 times -1 squared. And then this would be b times -1 squared. And then d times -1 times 1 squared. And then plus e times 1 squared. So we end up with an equation of a minus b, oops, not minus, plus b minus d plus e. Okay. Well, we already know a couple of these. We know that e and b were both 1/4. B was equal to 1/4, and E was equal to 1/4. So we're getting a little closer. We get that 1 equals to A plus 1/4 minus D plus 1/4. 1/4 plus 1/4 is 1/2. So we get 1 equals to A minus D plus 1/2. So moving that to the other side, we end up with 1/2 is equal to A minus D. Okay, so let's see, what else could we substitute? We've tried 0, we've tried B, C. Let's see, what else would be a good choice to substitute? So I can't really think of anything else that would be like a nice, convenient choice to substitute. Nothing that's obvious pops to mind. Other candidates are sometimes like a half or a negative 1/2 or something else that would be easy to see. So I think we're going to have to kind of blend both ideas and go back to this guy over here and at least begin with matching up some of them, right? We don't have to do the whole thing, but at least begin by matching up the biggest powers. So if I go back to this method, right? If that method had given all the values for me, I'd be really happy. But I'm at least going to think about the powers of 3. So if I had kept going this way, I would end up with w to the 3rd power minus 2w squared plus w squared minus 2w plus 1. All of that gets multiplied by the a, right? Just foiling this whole thing out. And then I end up with the b's. So I'm going to make some room here. This will be plus b. And we were done foiling that out. So that's just going to be w squared minus 2w plus 1. Okay, and now I got to FOIL these guys out. So plus d times, and we get w to the 3rd power plus 2w squared plus w minus w squared minus 2w minus 1. That's foiling out all of these guys. So let's put it in there. This was foiling out that. And this guy is this guy foiled out. And then finally the last term there, and we already finished the foiling, so we don't have to do anything special with it, plus w squared plus 2w plus 1. Whew, okay, so big, ugly, nasty thing, but if we just focus on regrouping just the powers of 3, maybe that might be enough. And I know there's 1 there, right? So it'll be a times this. There are no powers of 3 there. There is 1 power of 3 right there. And there are no powers of 3 over there. Okay. So I know that if I regroup all of this, I'll end up with 1 is equal to, and then we'll have an a plus d powers of 3. And then the powers of 2, whatever they are, there's going to be some complicated thing there. I know that there's a minus 2a, for example. I know that there's a plus b, and then there's a w squared there, plus something with a w, plus some constant. Right? So I could keep going and find the rest. But if I just stop there, and maybe that's enough, I don't know. And then looking on the left-hand side, remember that because there is no powers of w on the left-hand side, that must mean that there is a 0 w cubed over there. And there's a 0 w squared there. And there's a 0 w plus 1. Good. Questions? Okay, so then what I can conclude is that we got another statement. A plus d must be equal to 0. Right? I can conclude that a plus d must be 0. Okay, that coupled with this other piece of information that we had from the other technique, we had that a plus d must be equal to 0. And I also know that a minus d must be equal to half. So a must be equal to negative d. And then I can just do a direct substitution here. And get that positive 1/2 must be equal to negative d minus d, which means that negative 1/2 is equal to negative 2d. Okay. Multiply both sides by negative 1/2 times negative 1/2. These guys cancel. And I get that d must be negative 1/4. Good. So we have the other one. And finally, now that we have that d must be negative 1/4, we can come back over here, plug this into there, and get that a is equal to negative 1 times d, and d was negative 1/4, so a must be equal to positive 1/4. So looks like we have them both. We have everything we need. You know, it's easy to get lost in these questions. They're really, really big, so keep good notes. So A is positive 1/4, B is positive 1/4, D is negative 1/4. Wow, so they're all 1/4s, and they're all positives with the exception of D. Right, so going back to the original thing over here, this is going to be 1/4, 1/4, 1/4, negative 1/4, and 1/4. Good. Okay, so let's rewrite the whole thing over here now. Let's take this way over there. You know what? The screen doesn't like going to the right, so forget it. Let's go below. Let's start over again. Okay, so we had the integral of t1 over t squared minus 1 squared dt. And then I said, I don't really like to work with t's. I changed it over to w. So I said, let's rewrite this as 1 over w squared minus 1 squared dw. Okay. So then this is now going to be equal to these fractions. We had a w plus 1. Oh, I have to put them in the same order as I did up here. Plus 1 and then plus 1. Yep. Plus 1 and then w plus 1 squared plus and then w minus 1 plus and then w minus 1 squared dw. And after a lot of work, we saw that this guy is equal to positive 1/4. This guy is equal to positive 1/4. The only one that's negative is d, and d is the one that's over the w minus 1. That's this one. So minus 1/4 and then positive 1/4. Like that. Good. This one's easy to integrate. This one is a little trickier. Not too bad. Maybe a quick little u substitution for it. Okay, so let's simplify these. So this will be equal to 1/4. Let's just put that out there. Integral of 1 over w plus 1 dw plus the integral of, let's put the 1/4 out there again. We have 1 over w plus 1 squared dw minus 1/4 integral of 1 over w minus 1 dw plus 1/4 integral of 1 over w minus 1 squared dw. Good. Okay, so that one's easy. This one, you might want to think about it as like a quick little substitution here. Or you can just kind of power through it. Remember that, again, we've seen this before. If we have w to the power of 2, then we can rewrite this as w to the negative 2. And so a derivative that would give you this would be w to the negative 1. Except that there's an extra minus 1 we have to deal with, right? We just did this above somewhere, so hopefully that part will be easy. Okay, so this is just going to be equal to 1/4 ln of w plus 1. Takes care of this one, right? The derivative of this is 1 over this. Good. And then going to be -1, this the power of -2, which is that guy. So we need that extra -1 to balance it out, because that's not supposed to be minus. Okay. Minus 1/4 ln of w minus 1 plus, and then this one is the same as that one, so this will be plus 1/4 -1 times w minus 1, the power of -1, right, plus a constant. So we can just simplify this just a little bit. Combining these two, usually we like to combine this one and this one, keeping in mind that it's a subtraction and that there's a 1/4 constant. So I'm going to combine those into 1/4 ln of absolute value of, and it'll be w plus 1 divided by w minus 1. That takes care of this whole thing and that whole thing. And then minus 1/4 times this, so minus 1/4 times w plus 1 minus, and then same thing over here, 1/4 times w minus 1 plus a c. And, well, it would be rude not to combine these. So, I mean, you could stop here, but they're just so close to being something we can combine. So it would look nice if I did this, w minus 1 times w minus 1, and then w plus 1 over w plus 1. And then that would give me the following. This would be 1/4 ln of w plus 1 over w minus 1. And then this would be minus w plus 1, distributing this minus through there, all over, no. So in this case, since I distributed a minus, would be a plus there, and then all over 4 times w plus 1 times w minus 1, and then plus, and then distributing that minus, we get minus w minus 1 all over 4 times w plus 1, w minus 1, plus a constant. Okay, so now they have the same denominator. We get to bring them together, one big happy fraction. And so we end up with 1/4 ln of w plus 1 over w minus 1 plus, and then there's a giant fraction here where the denominator is going to have a 4 times the product of these two, which we already know is equal to w squared minus 1. And then the numerator has these two, and so we'll end up with a minus 2w, and the plus 1 and the minus 1 cancel. So just minus 2w plus a constant. And so now these two would reduce to give me my final answer, 1/4 ln of w plus 1 over w minus 1 absolute value minus w all over 2 w squared minus 1 plus a constant. Come on. Plus a constant. Good. Questions? And I think this is what the answer has, except, what did they do? Oh, well, okay, so same answer, but if you look in the back of the book, they factored out the 1/2, therefore they left that there, and then they distributed that minus through here. So same thing. So the book has 1/4 and then a giant bracket, so they factored that out. Ln of w plus 1 over w minus 1. And then since you just factored out the 1/4, we leave that 2 there. So plus 2w. And then that minus, they distributed in the denominator to write it as 1 minus w squared. Not sure why they prefer it written that way. And then plus some constant. Plus some constant. Now, this constant, right, we factored out the 1/4, so this constant and this constant would actually be different. Right? It doesn't really matter. Constant is a constant. And so that's what the book has. Same as this, same as that. Just a little bit of algebra. Okay, any questions? Yeah, ugly stuff, right? So this section in particular has really big, really complicated looking problems. Don't let this discourage you too much. It's not the case that things just build from here and they get uglier and uglier and uglier moving forward. That's not really the case. So we're gonna move on to other things, and this will be. This isn't something that's an omen of everything to come in calculus. But yeah, this section has some ugly, ugly questions. Any questions or comments or anything on this one? Number 21 on Chapter 7, Section 4. No? No? Okay, so just be really, really neat and organized. More neat and organized than I can be with this thing. If we were in the classroom, this would be a great time to take advantage of all those boards all around the room, and we can like surround you with math and take advantage of every square inch of all 4 boards all around you, and it would be kind of written out in one nice, neat, organized way. But it makes it really hard with this technology to do that for me. Haven't quite mastered it yet. But at any rate, on your own notes, be careful to be very, very neat and organized. This is the kind of problem where if you're messy, you're going to get lost. You're going to get confused. You're going to forget what you were doing, where you were going, what equation from where, and it can get really, really, really messy. Okay, so don't be afraid of using a lot of space and being really neat and organized. Good, good, good. It's not a nightmare. They really are this long. That's this section for you. Good? Questions, questions, questions? Okay, we're going to stop there for now. Keep working on homework. You should be able to do everything from the first 5 sections now. The 5th section doesn't have any new information. There really isn't anything new to cover. It's just like a moment to pause and think about all the integration techniques that we've been looking up to now, and kind of taking a moment to try and figure out when one technique applies and when another technique applies. So it's just a little bit more practice. So you should be able to work on those. Next week, I will do some of those problems, some more problems from 7.5. So just walk through and answer some of those things. I might do some over the weekend, so look out for some posts if I do some extra ones. And then we're skipping 7.6 and 7.7 and moving on to 7.8. So there's really only one more section of new material in Chapter 7. So we'll definitely get that done by next week. And then the week after that, toward the end, we'll have our first test. So I'm looking at somewhere in the neighborhood of October 1st or 2nd, something like that, is when we have it. Okay, so keep that in mind as you kind of set up your own schedule of things and kind of bring yourself up to date on the homework and everything. Okay, if you run into a problem with one of the homework exercises, send me an email let me know which one you're having trouble with, and that might be one that I record on and show you a nice worked out solution for it. Okay, so make sure you try the homework and send me questions if you have them. Okay, good. Questions, comments, issues? All right, good time to sign off then. Have a good weekend, full of math. Hang in there.
Thank you, Professor. Have a good weekend.
All right.